Hello everyone, welcome back. In this video, we will be doing section 3 of chapter 4, how derivatives affect the shape of a graph. So the whole point of this chapter is to analyze graphs to find global maximum, global minimum, or absolute maximum, absolute minimum, and relative maximum or relative minimum, which also mean local maximum or local minimum. And, and then we have seen mean value theorem, Rolle's theorem, mean value theorem. And in this section, we are going to see some characteristics of a graph. So you have already seen some of which you have seen that in pre-calculus level, which means how to get the domain, how to get the range, what are the horizontal asymptotes, what are the vertical asymptotes, is there any symmetry for the problem, for the graph, all those things. Now in this one, we are going to go deeper into the topic and see how calculus helps in determining whether the function is increasing or decreasing, or concave up, concave down, what is the local max, what is the local min, etc. Okay. So how derivatives affect the shape of a graph. So if you look at this graph, the blue graph, then the tangents are shown at these points. If you look at the sketch here from A to B, you notice that you have throughout from A to B, the slopes are positive. The tangent slopes are positive. Same way from C to D. So in this part, and in this part, you notice that the slopes of the tangent lines are positive, which is a characteristic of a function being increasing. And if you notice this part of the graph, B to C, here the tangent, slope of the tangents are negative. The slope of the tangents are negative. Here from A to B and C to D, the slope of the tangents are positive. Okay. So from between A and B and between C and D, the tangent lines have positive slope, which is f prime x more than 0. Between B and C, the tangent lines have negative slope, which means f prime x less than 0. So this leads to defining increasing and decreasing test. If f prime x is more than 0 on an interval, then f is an increasing function in that interval. So the derivative determines the nature of the function. If f prime x is less than 0 on an interval, then f is decreasing on that interval. So this is known as increasing, decreasing test. So what is the first derivative test? Suppose that C is a critical number of a continuous function f. What do you mean by critical number? Recap from the previous section. A number is said to be critical if the derivative is equal to 0 or does not exist. If f prime changes from positive to negative, the sign of f prime changes from positive to negative at C, then f has a local maximum. F has a local maximum. At C. If f prime changes from negative to positive at C, then f has a local minimum. At C. If f prime does not change in sign, f prime does not change in sign at C. For example, if f prime is positive on both ends of C, both sides of C, or negative on both sides of C, then f has no local maximum or minimum at C. In the picture one, f prime at this point C, you notice that f prime x changes from positive to negative. So on the left side of the peak, the function is increasing. On the right side of the peak, the function is decreasing because the slopes are positive and negative respectively. So wherever the sign of the derivative changes from positive to negative, then there is a local max, local maximum point. Now, local minimum. The function decreases and increases in this graph at C. So it changes from negative, the derivative changes from negative to positive. Then there is a local minimum. So there is a valley. So in this picture, in figure 3, there is no change in sign. At the point C, to the left of C, f prime x is positive. To the right of C also, f prime x is positive. So there is no local max or min. Same way at C, to the left of C, f prime x negative. To the right of C also, f prime x negative. So there is no local max or min. So it should change from, the f prime should change from positive to negative, then there is a local max. F prime x should change from negative to positive, then there is a local min. Now, what does f double prime, the second derivative, say about the graph of f? The second derivative. What does the second derivative say about the graph of f? Figure 5 shows graphs of two increasing functions on AB. So there is an increasing function here, there is an increasing function here. And figure 6 shows figure 5 with the tangents drawn. And in A, the curve lies above the tangents, and F is called concave upward on AB. So in figure 5, you notice that in this graph, if you draw the tangent lines at every point, that the entire graph will be above all of its tangent lines. In the right side of 5, you notice that all the tangent lines are above the curve, are all above the curve. So it's known as, in this one is concave down, this one is concave up. So in this picture, you notice that the entire graph is all above its tangent lines in figure 6. Similarly, for concave downward graph, for this picture, the entire graph is below all of its tangent lines. The graph of f lies above all of its tangent lines on an interval I, then f is called concave upward. So if it is all, if the entire graph is all above its tangent lines, it is said to be concave upward. If the graph of f lies below all of its tangent lines, then it is called concave downward. So in this picture, you notice that between the points A and B, the graph is concave down. Between the point B and C, it is concave up. Then between C and D, it is concave down. Between D and D, it is concave up. That it is concave up. This piece is concave down. Then between E and P, it is concave up. Concave up. Between P and Q, it is concave down. All right. What is concavity test? If f double prime x is positive for all x in the interval I, then f is concave upward on the interval I. If f double prime x, the second derivative is less than 0, negative, for all x in I, then the graph is concave downward on the interval I. A point P on the graph y equal to f of x is called an inflection point where the concavity changes direction. One is concave up to concave down, or from concave down to concave up, wherever the figure changes concavity, such a point is said to be an inflection point. If f is continuous there and the curve changes from concave upward to concave downward, or concave downward to concave upward. This definition leads to the second derivative test. Suppose f double prime is continuous near C. So look at this picture here, figure 10. If f prime C is equal to 0, and f double prime C is more than 0, at that point C, if the second derivative is positive, then the graph is concave upward. If it is concave upward, then there will be a valley, which is a local minimum. There is a local minimum at C. If the first derivative is 0 and the second derivative is negative at a point C, then f has a local maximum at C. This is second derivative test. So if I summarize this, so a function is concave up if it lies above all of its tangent lines. It is concave downward if the graph is below all of its tangent lines. That is number one definition. Then a point is said to be an inflection point wherever the concavity changes, either from upward to downward or from downward to upward. What is the second derivative test? The first derivative equal to 0, then f double prime C is more than 0. The second derivative is positive. That means together it means that it is concave upward. Then it makes sense to say that it has a local minimum at C. Concave upward will have a valley. Concave downward will have a peak, which is local maximum at C. F prime C equal to 0 and the second derivative less than 0. So let's try problem number 5 is done in the video, section video. Please check that. Problem number 5, and also one more problem. And this problem is also done in the video. So video problems are number 5 and number 23. Right. Please check those problems. Let's try one of these, either 37 or 47. Maybe we can try number 47. So what is it asking? Find the intervals of increase or decrease, meaning what is the interval where the function is increasing? What is the interval where the function is decreasing? So sometimes it's not necessary or always that you should have answer to both. Sometimes the function is only increasing. Sometimes the function is only decreasing. So there are cases like that. So find the intervals of increase or decrease. Find the local maximum and minimum values of f. Find the intervals of concavity and inflection points. Use the information from part A to C to sketch the graph. Check your work with a graphing device if you have one. So let's try number 47 here. First, we have to determine for part A, the intervals of increase or decrease. What are the intervals where the function is increasing? What are the intervals where the function is decreasing? So we know that by increasing, decreasing test, which is known as ID test, we know that f prime is more than 0 would mean that f is increasing. F prime less than 0 would mean f is decreasing on that interval. So let's start off with the derivative of the function. So it is 1/2, which is a constant, x to the power 4, which is 4x cubed, minus derivative of 4x squared, which is minus 8x, derivative of 3 is 0. So it's just 2x cubed minus 8x. If you simplify, if you set that to 0, you get 2x times x squared minus 4 equal to 0, which will mean 2x equal to 0, x squared equal to 4, which would mean x equal to plus or minus 2. So x equal to 0, x equal to 2, x equal to negative 2 are the critical numbers. Because this is a polynomial, this function is a polynomial, so there is no, it's everywhere differentiable. So the derivative exists, and it's equal to 0 will give us x equal to 0, x equal to 2, and x equal to negative 2. So let's plot them, these points, x equal to 0, x equal to negative 2, and x equal to positive 2. And we have a negative infinity here and positive infinity here. We are checking whether in which interval f prime x would be positive, right? So let's take a test point here. Let's say negative 3, a test point here. Let's say negative 1, a test point here, positive 1. Test point here would be positive 3. So let's substitute into either the original function. We are going to substitute into, we are going to see whether f prime x is more than 0. But what is f prime x that we computed? F prime x that we computed is 2x cubed minus 8x. We have to see whether f prime x is more than 0 or not. So f prime of the test point negative 3. Just 2 times negative 3, the whole cube, minus 8 times negative 3. So we are taking this function, we are plugging in the value negative 3. So which will be negative 27 times 2, which is negative 54 plus 24. That will be a 30. So that will be negative 30. So f prime of negative 3 is negative, which means in this interval, your graph f prime, f is decreasing in this interval. And let's take the test point negative 1 and we'll evaluate f prime of the test point, which is negative 1. So 2 times negative 1 the whole cube minus 8 times negative 1, which is negative 2 positive 8, which is 6. So you notice that f prime is positive in this interval. So f is increasing in the interval negative 2 to 0. So we have these points here. So here f is increasing. Between 0 to 2, the test point is 1. So if we consider f prime of 1, which is 2 times 1 cube minus 8 times 1, it is 2 minus 8, which is negative 6. So between 0 to 2, you're only choosing a test point in that interval. The behavior of the test point is same as any point in that interval. So here, because f prime 1 is negative, the function is decreasing here. Between 2 and infinity, our test point is 3. So f prime 3. So 2 times 3 cube minus 8 times 3. It's 27 times 2, which is 54 minus 24, which is equal to positive 30. If it is positive 30, f is increasing. So we have found out the interval where f is increasing, where f is decreasing. So we have to write that for part A. F is increasing on the interval -2 to 0 union 2 through infinity. So f is decreasing on the interval -infinity through -2 from the picture, union 0 through 2. Okay. We know that if the function decreases and then increases, that will be a valley, which will be local minimum. If it is increases and then decreases, there will be a peak, which is local maximum. So we are aiming for those values in the second part of the problem. The second part, it's asking, find out the local max and local min values. So here we notice that -infinity to -2, the function is decreasing. And then from -2 to 0, it is increasing. So you notice that this point, -2, where there is a local minimum, the local minimum. Then increasing to decreasing, so 0, at which it is local max. Decreasing to increasing, so again, there is a valley here. Local min. Okay, so we can write that as -2, f of -2 is a local minimum point. Same way, what is the other minimum point? So this is actually local min, right? Decreasing to increasing. At 2, so 2, f at 2 is again local minimum point. What are the local minimum values? So we have to find out what this -2, what is f of -2? We have to plug in f of -2 and f of +2. So if to plug in -2 and 2 into the original equation. So if you do f of -2, f of -2, you take the original function, which is 1/4 of x to the power 4 minus 4x squared plus 3, 1/2 of x to the power 4 minus 4x squared plus 3. We're going to plug in -2 in the place of x. Which will be even exponent, so it's all positive here. So it becomes only 2 to the power 4 over 2, which is 2 cube, which is 8, minus 4 times 4, that will be a 16, plus 3. So it is actually 11 minus 16, which is a -5. So we notice f prime of -2 is less than 0. F of -2 is less than, it's equal to -5. So what is f of +2? This is an even exponent. F of +2 should also be the same half 2 to the power 4 minus 4 times 2 square plus 3. That will be 8 divided by 2, 16 divided by 2, that will be an 8 minus 16 plus 3. So that's also negative 5. So going back to this particular step here, we say negative 2, comma negative 5 is the local minimum point, and local minimum value is always the y coordinate, which is negative 5. What about the local maximum? The local maximum, we pointed out 2 points. So here, increasing to decreasing, it's only 1 point, which is local max, which is happening at 0. 0, it's happening. The function is increasing and then decreasing. So f at 0 will be the local maximum value. So 0, f of 0 is a local maximum point. What is f at 0? So which is 1/2 x to the power 4, which is 0 to the power 4, minus 4 times 0 square plus 3, which is equal to 3. So 0, 3 is the local maximum point, and local maximum value there is nothing but the y coordinate, which is 3. Now, now we are going to discuss about the concavity. That is part C. We have to find out where the graph is concave upwards, concave downwards, and then that leads to inflection points. So we have to use the concavity test, which is nothing but the second derivative. What does the concavity test say quickly? We'll check that. So if the second derivative positive, then it is concave upward. The second derivative negative, it is concave downward in that interval. So let's see now what the second derivative is. So we already did the first derivative. We'll start there. First derivative turned out to be 2x cubed minus 8x. I'm looking at this step, 2x cubed minus 8x. So it is 2x cubed minus 8x. So the second derivative is going to be 2 times 3, 6x squared minus 8. So if you take 2 outside, which is 3x minus 4. So if you set the second derivative to 0, you get x equal to 4 by 3. Now you are going to divide the interval with 4 by 3, just 4 by 3 there. So there is 1 to the left of 4 by 3, 1 to the right of 4 by 3. What is the nature of f double prime in the interval? This will be 3x squared minus 4. So it will be x squared equal to 4 by 3, or x equal to plus or minus square root of 4 by 3. Right? Or it is plus or minus 2 divided by square root of 3. You can write either way. Now, my division should include negative 2 over radical 3 and positive 2 over radical 3. So if we just make a, if we find out the value of negative 2 over radical 3, so it is 2 divided by square root of 3. So 2 divided by square root of 3. That is 1.15. So if you look at in this graph, it is negative 1.15. It's positive 1.15. So I have to pick a value to the left of negative 1.15 to look at, find out what is happening in this interval. Then in this interval, negative 2 over radical 3 to 2 over radical 3, that interval, and then the interval 2 over radical 3 through infinity. It's negative 1.15. So if I pick, say, negative 2 in this, here the test point is negative 2. Here the test point can be taken as the origin. Here the test point can be taken as positive 2. So because we are discussing concavity, we are looking for the second derivative at the test point. We said that the second derivative was equal to 6x squared minus 8, evaluated at x equal to negative 2. That is 6 times negative 2 squared minus 8, so which is 24. The 6 times negative 2 squared, which is 24, minus 8, which is a 16. So what does it say? It is positive. Because it is positive, the graph is concave up in this interval. So we'll pick a 0 as a test point in the interval negative 2 over radical 3 to 2 over radical 3. So which is 6 times 0 square minus 8, which is negative 8, less than 0. So if the second derivative is negative, it is concave down in that interval. Now you have to pick a value to the right of 2 over radical 3, which is more than 1.15. We can pick 2. F double prime at 2 equal to 6 2 square minus 8. So 24 minus 8, that will be a positive 16. So which is F is concave up. So in this picture, you notice that here the concavity changes. At negative 2 over radical 3, the concavity changes. Same way at 2 over radical 3, the concavity changes from down to up. So those are the inflection points. So x coordinates of the inflection point. So we have to find out the inflection. Before that, we will write down where the concavity occurs. F is concave up on the interval negative infinity through negative 2 over radical 3. Also union 2 over radical 3, comma, infinity. This is for concave up. Where is it concave down? F is concave down on the interval negative 2 over radical 3 to 2 over radical 3. So what is the inflection point? Wherever the concavity changes. The inflection points are negative 2 over radical 3, f of negative 2 over radical 3, because the concavity changes there from concave up to concave down. Same way, another point is 2 over radical 3, f of 2 over radical 3. So what is f of negative 2 over radical 3? F of. So you have to go to the original function and substitute. What is our original function? Which is half x to the power 4 minus 4x squared plus 3. So half x to the power 4 minus 4x square plus 3. So I substituted these into the original equation given in the problem. So you can also use the graphing calculator for this to compute. So plug in y1 equal to the original function, 1/2 of x to the power 4 minus 4x square plus 3. Compute this, plug in this function into y1. Then you do in the home screen, y1 of negative 2 over radical 3. So I can quickly show that, calculate the feature here. So you'll be going to y1 and plug in this 1/2 x to the power 4. So it is x to the power 4, x to the power 4 divided by x to the power 4 divided by 2. It is half of that. Then you go on the right, plug in minus 4x square minus 4x square. So we will do this one more time because we can use the numerator over denominator feature. And then it won't be a mistake at all. So x to the power 4 on the numerator, and the denominator is 2. Then you go to the right arrow and then plug in minus 4x squared. Then you plug in plus 3. So we have stored this function in y1. Then you go to the home screen by doing second and quit. It takes you to the home screen. In this one, you want to evaluate the y1. So click on variables, yvar. Then you click on y1. And you want to evaluate this at negative 2 divided by radical 3. Close the parentheses. That is negative 13 over 9. It is negative 13 over 9. And also we have one more inflection point, which is happening at 2 over radical 3. So it's f of 2 over radical 3. So which is 1/2 2 over radical 3, the whole power 4 minus 4 times 2 over radical 3 plus 3, which will be again negative 13 over 9. Because the function is after all an even function, because of the power 4 square here, makes it even. So whether the value x input is a negative value or a positive value, you're going to get the y coordinate the same. So the inflection points, we call it IP, are both x coordinates are negative 2 over radical 3 and positive 2 over radical 3. So it's plus or minus that. And then the y coordinate for both of them seems to be the same. So which is negative 13 over 9. So thus we have done all parts except the graphing part. Now we will take care of the graphing part by using all the information. So from what we have seen so far from part A, B, and C, from 1, 2, and 3, so the graph is decreasing on the interval negative infinity to negative 2 union 0 to 2, and increasing on the interval -2 to 0, union 2 through infinity. The second part of the problem, we have seen the local maximum point is 0, 3, and the local maximum value, which is the y coordinate of this point, which is equal to 3. Then where is it is concave up from -infinity to -2 over radical 3, and from 2 over radical 3 through infinity, and it is concave downward on the interval -2 over radical 3 to 2 over radical 3. The inflection points are the points where the concavity changes, and it is happening at the x coordinates 2 over radical 3 plus or minus. And when you find out the y coordinate, turns out to be the same, which is -13 over 9. So we have to put all this information together. If you notice, the points that we need are -2 to 0, then the y coordinate 3, then the x coordinates -2 over radical 3, and -13 over 9, which is the y coordinate. So in this picture, you notice that this part, we have the graph is decreasing from -infinity to -2, and then increasing from -2 to 0, decreasing from 0 to 2, and increasing from 2 through infinity. Then it is concave upward up till the inflection point. The inflection points are plus or minus 2 over radical 3, which we saw as plus or minus 1.15. So somewhere between 0 and 1, both sides of the origin. And the negative, it has a negative y coordinate, which is -13 over 9, which is again -1 point something. So we have placed those inflection points there. And we have seen the local maximum point, which is this 0, 3. Local maximum point. We have shown the inflection points on the graph, and we have written them. So this is how the graph is sketched using the calculus techniques. You might have done the same kind of graph earlier in the pre-calculus level, just by getting domain, range, and symmetry, and then even odd nature asymptotes and so on. In this problem, we see them. We do the same graph by using calculus techniques. So that completes this section. So as I said, check the videos for some of the problems I have done in the section videos, namely 23 and problem number 5 in the section videos. Hope this video helps, and watch my next video on 4.4, which is L'Hopital rule.